This video is going to introduce the definite integral. So what is the definite integral? Well, it's a limit of Riemann sums. Let's recall what a Riemann sum is. So if you have a function f, and we start with an interval a to b, then we can divide the interval up into smaller subintervals. So we can divide it. And we want to see what the contribution of f is, which you may think of as a rate, to each subinterval. So remember the formula for Riemann sums. For example, the left-hand sums goes as follows. We take the value of the left endpoint of each interval. This left endpoint is t0. This would be f of t0 times the length of the subinterval. If all these subintervals have equal length, then that length is delta t equal to b minus a divided by the number, n is the number of subintervals, so delta t. That's the contribution for the first subinterval. Then we add to that the contribution for the next subinterval, which if we're doing left-hand sums, we'd start at t1 times the length of that subinterval, which if they're all equally spaced is again delta t, where delta t is given by b minus a. Here n is the number of subintervals. And we continue. The next subinterval, this interval, would be given by, well, the value of the function f of t2, because we're taking the left endpoint, because we're doing left sums, times the length of this interval, which again is delta t. And then we continue this onwards. F of t3, the next left endpoint times delta t. We continue all the way until we get to the very end. If b is tn, then the previous point will be tn minus 1, so we take that left endpoint for this interval. So we have f of t n minus 1 times delta t. So that's a review of what the left Riemann sums are. And we could do something similar with the right Riemann sums. We would just use the right endpoint of each interval. We would start with f of t1, f of t2, f of t3, f of t4, all the way to, this time, the right endpoint, which is tn. So that's the left Riemann sums. And we could do similar for the right. Now, the actual value that we're trying to estimate with Riemann sums, we get a better approximation. Here's the key. A better approximation is obtained if we use ever smaller intervals. This is sort of a limit. So if we take, in particular, if we take the limit as delta t goes to 0, or in other words, if the number of intervals gets very large, then delta t goes to 0, of the Riemann sums, either left or right, this will actually equal the desired actual value that we're trying to estimate. Now this actual value, we can set up, we have a certain notation for this. This limit of the Riemann sums is going to be the actual value we're approximating. we have notation. We write this integral of a to b of whatever function we're given to start with times dt. Okay, so that's kind of this is the key point for this section, is to realize what this notation means. So let's break it apart. This is supposed to be the limit of the Riemann sums. It's the actual value of the integration problem we're trying to do. It's what it's what we're estimating with Riemann sums. Now here, let's break down the notation. We start at a, that's the left endpoint of our interval. The right endpoint will be b. This is the function that we're integrating, usually at some rate of change. Then dt. What is dt? Well, dt is supposed to be the length of a subinterval. Now, of course, our subintervals, because we've taken delta t to 0, our subintervals are infinitesimally small. So we replace delta t with dt. This is now an infinitesimally small length. We still have a product, though. We have a product of the height times the width of the subinterval. It's just the widths are infinitesimally small. Okay, so this is called, in words, the definite integral of the function f of t over the interval a comma b. In other words, or in a shorthand, it's just the integral of f over ab. So integral f over ab. Okay, so for example, we could try to express the definite integral. The total distance traveled by athlete who is traveling at 0.5 meters per second over interval. He starts at 0 to t. Oh, not 0.5, let's say f of t. It's a function of time. Over the interval, say 0 to 6. So 6 seconds, 0 to 6. He's traveling f of t meters per second. I don't know what f of t is. Express this using an integral. Okay, so again, we have some athlete. We want to know the total distance he travels. What we know is his speed. He's traveling at this speed, f of t meters per second, over an interval of 6 seconds. How do we express that as an integral? We just write, in terms of notation, we write 0, that's the starting point. The end point is 6, 0 to 6. His speed is f of t, and then just write dt to indicate we're actually taking an integral, that we're doing Riemann sums, this times delta t. Okay, and then there's a graphical expression for the definite integral, so we should explain that. It again has to do with area. If we have a function f of t, and recall that the left-hand sums corresponding to areas of rectangles. So here are the left-hand sums. These are the left-hand endpoints, the values of the function at those points. And this total sum gives us basically the accumulation of our changes. Now notice that the area under these the area of these rectangles is very close to the area under the curve. So the area under the curve here is given by this. It's this area. And the area under the curve is very close to the total sum of the areas of these rectangles. And in fact, if we make the intervals smaller and smaller, as we do when we compute the definite integral, if we take delta t goes to 0, then the area is not only approximated, it's actually equal to the limit of the Riemann sums. So ultimately what we end up with is that the definite integral from a to b of f of t dt is equal to the area under the graph. So this yellow area under the graph of the function, that's actually equal to this limit of Riemann sums, this definite integral. So that's a graphical interpretation of the definite integral. I should point out that this graphical interpretation really only works if the function f is positive. That is, if the graph of the function is above the x-axis. If f dips below the axis, things become slightly more complicated. Little rectangles here that give us the Riemann sums, they actually have a negative height. So the contribution below the axis is negative. So you can compute the area under the axis. That always counts negatively. So if this area is, say, 2, then this is minus 2. Whereas if we're above the axis, and say this area is 1, then it's a plus 1. This area might also be plus 1. Okay, I'm just giving arbitrary values. This plus 1, maybe this is minus 2, maybe plus 1. But whatever they are, the point is that the total integral, the integral from a to b of f of t dt, if this is a, this is b, this is going to be 1 minus 2, 1 for this part, minus 2 plus 1. So altogether, in fact, for this example, the integral is actually 0 if these are the values 1, 1, and this area is 2. Okay, this ends our introduction to the definite integral.